last lecture, we have given many examples of the vector spaces and seen that most of them they are the metric spaces. For example, CAB, LP, L infinity, these are all vector spaces, and the metric which we have defined on it in the usual way, the distance between the 2 points, they form the metric space. But so far the notion of the distance d and the addition and scalar multiplication which you are using in formation of the vector space for these classes does not have any relation. So, the definition of the metric space or the way in which we are getting the metric space will not be a very fruitful things. We cannot develop a fruitful theory when we start with the concept of the distance notion in this fashion. So, we are interested to define the metric in some other way which has a relation between the addition and scalar multiplication as well as the notion of the distance. So, for this we introduce a concept of the norm which has a relation with plus and dot, and then with the help of the norm we will introduce the notion of the distance on it, so that we can get a useful theory for further developments. So, before it is the norm space. We define the norm space A norm space is a vector space with a norm defined on it. A Banach space is a complete normed space where the completeness complete in the metric introduced or defined by norm. So, what is the norm space? It is a vector space X with an operation dot plus and dot, vector addition and scalar multiplication, and a norm is introduced on it. So, this complete structure we call it as a norm space, and in short we denote as this. We understand X with the operation plus and dot, and norm is a norm defined on it. Banach space is a complete norm space. Complete means every Cauchy sequence in it must be a convergent one. So, when you say Cauchy sequence converges, it converges in the norm of X, all in the metric introduced with the help of norm on it. Clear? So, this involves the concept of norm first. Vector space we have already introduced. Now, what is this norm? We define the norm as as a norm on a real or a complex vector space capital X on a real or complex vector space capital X is a real valued function on X whose value at an X belonging to capital X is denoted by norm of X, which satisfies the following properties, which satisfy the following which satisfies following properties. Okay. So, a norm on a real or complex vector space X is a real valued function on X whose value at n x is denoted by norm X, which satisfy the following properties. The properties are: first property we say n 1, that is property of the norm. The norm of X is greater than equal to 0. It cannot be a negative quantity. Then n 2, the norm of X equal to 0 if and only if X is an identically 0 vector, theta is a identically 0 vector or 0 element. Okay. Identically 0 element. N 3, the third property is the norm of alpha x equal to mod alpha into norm of x, where alpha is a scalar quantity and this alpha belongs to the field of the vector space X. If X is real, the alpha will be real. If X is complex, the alpha will be a complex. And last property is the norm of x plus y is less than equal to norm x plus norm y. X plus y is norm. So, if these four properties are satisfied, then we say this now X with the norm is a norm space. Then then X with this is a norm space. Okay. So, basically what we are getting is that norm is nothing but a function from a vector space X to R. You can say the R 0 non-negative real quantity, a real valued function, such that the image of X goes to norm of X. Each point X in image X for any X belongs to capital X, and that this norm satisfies these four properties. So, when this satisfies, we say it is a norm space, and the corresponding space is called the norm space. If we look this vector space X, a set of vectors in the 3-dimensional plane, suppose R 3, then we have these properties which are enjoyed by vectors in a 3-dimensional plane. First thing is the length of any vector a b, the length of this vector a b can never be 0 or negative. Length of the vector can never be negative. So, if I denote the length of the vector a b as x mod of x, this is the length of the vector AB, then this length can never be a negative. It means it is always be greater than 0 or at the most 0 when B coincide with A, that is the way x becomes 0. So, the first property says that it is the generalization of the length of the vectors. Second property is first and second. Third property says if suppose I multiply a vector A B by a alpha, where alpha is a scalar quantity. So, mod of if alpha is less than 1, then it will reduce, alpha is greater than 1 or mod alpha is greater than 1, less than 1. So, accordingly it has a length is changing. So, what the effect? It will affect the mod of alpha into the length of the vector. Then third property says that the sum of any two sides of a vector in a triangle can never be less than the third side. So, third side, this is our vector x, this is vector y, this will be the x plus y vector. So, sum of this two sides of the vector will always be greater than equal to the length of the third side. So, that is this property of the triangular property holds. So, this concept of the norm which we have introduced is nothing but the concept of the length of the vectors in a general vector space. When we go for the R3, we get a vectors and the length of the vector has been generalized this concept to an arbitrary class capital X, which is a class of all the elements, maybe a sequence, maybe function which forms the vector space. So, the norm generalized the concept of the length of the elements of a vectors in a arbitrary vector space. So, that is the concept. Clear? Another thing which we cannot here is that if we introduce d of x y as the norm of x minus y, where x and y are any arbitrary elements of x, then you will see all the properties of the matrix are satisfied. First is d of x y will always be greater than equal to 0, because the norm can never be negative. Then if it is 0, it means x minus y must be 0. So, x must be equal to y. So, x must be equal to y. The third property, if suppose I interchange the x and y, instead of this I write by x, both will give the same value, because the interchanging x and y will not affect, because it is a non-negative quantity. So, negative sign will not affect. Okay. So, y minus x, it will remain that. Then other property of the d of x y is less than or equal to d of x z plus z, that also is satisfied. So, all this property which is equal to norm of x minus y, which can be written as norm of x minus z, z minus y, and that will be again less than or equal to norm of x minus z plus norm of z minus y, and that is equal to d of x z plus d of z y. So, the properties of the matrix are satisfied as soon as we introduce the concept of the matrix in terms of the norm, and this gives a matrix. So, x d becomes a matrix space. X d becomes a matrix space. Clear? It means every norm space is a matrix space. So, as a result you can say every norm space is a matrix space. Every norm space is a metric space. Clear? Because whenever you take norm, it can be converted into a metric. Okay. But converse need not be true. But converse need not be true. In general, That is, all the metric spaces may not be a norm space. For example, if we consider the class S, the set of all sequences, bounded or unbounded sequences, bounded or unbounded sequences of real or complex numbers and introduce the notion and define dxy as sigma one by 2 I is 1 to infinity mod of x I minus by I over 1 plus mod x I minus by I, where x is x I is 1 to infinity belongs to capital X, y which is y I is 1 to infinity belongs to capital X. Okay. So, if we look this metric D, then we have already seen that this forms a metric space, that S D will be a metric space. Is a metric space. We have already seen. Is it a norm space? The question is it a norm space? Okay. The answer is no. Why? It means those properties of the metric space which we have introduced, those property of the norm space, all the properties are not satisfied. That is, this property which we have introduced, the norm of x is greater than equal to norm x equal to 0, is a alpha x equal to this and so on, is not, all property may not be satisfying. So, let us suppose it is a norm space, it can be defined with the help of the norm. So, if it is so, then let us see the d of x 0, suppose it is the norm of x which is equal to sigma 1 by 2 I mod of x I over 1 plus mod x I is 1 to infinity, is it not? Because what is this norm x? It is the length of the vector. Okay. So, from origin you are choosing the distance. So, now let us suppose dxy x 0 can be written in terms of the norm as follows. Then what should be the norm alpha x? This is equal to what? Mod alpha x I, alpha x I. Now, can you take alpha outside from here? If I take alpha outside, it is not possible. It cannot be, this cannot be equal to mod alpha into sigma of this. It cannot be. That is, it is not equal to mod alpha into norm of x. Is it not? Because this is no. So, mod norm of alpha x is not equal to mod of alpha into norm of x. That is, norm alpha x is not equal to mod alpha into norm of x. So, the condition N2 or n3 fails. Therefore, S cannot be a norm space. So, S under this is not a norm space. So, though it is a metric space, but it is not a norm, or you can say the norm metric cannot be defined with the help of the norm. That is the metric D, that is the metric D cannot be defined or introduced with the help of norm as norm in the form norm, that is all. Dx y equal to norm of x minus y we cannot introduce, because it does not form. So, what we conclude that every norm space is a metric space, but all the metric space need not be a norm space. Clear? Now, let us see few example where it forms for both norm space as a metric space as well as the metric space. So, examples of norm spaces. So, first example, a Euclidean space, Euclidean space R n and unitary space C n. C n. R n means set of all n tuples one to n, where xi's are real and they are reals only, n tuples with reals, and the metric concept is defined as under root of this thing. So, here we are introducing the norm of x on R n, we are introducing as sigma I is 1 to n mod xi I square under root. Okay. R n is the set of all n tuples xi 1, xi 2, xi n, where xi's are real, and for each x belongs to R n, we introduce the norm as follows. Now, it satisfies all the condition of norms, that as because we have verified for the metric, and this metric D on R n can be defined as under root sigma I is 1 to n mod xi I minus eta I whole square, that is all. Okay. And that is the metric. So, R n with this norm is a norm space, and we call it this as Euclidean space, Euclidean norm space. Then C n is the set of all x, say eta I, okay, eta I, such that I is 1 to n, where eta i's are complex number, they belongs to the complex set C, they are complex numbers. Okay. And introduce on this the norm of x R n as sigma I is 1 to n mod of eta I square under root. Okay. Their eta i's are complex number. Complex eta I are complex numbers. Eta i's are complex number C.
But x norm x is defined on Cn.
Oh, this is Cn. This is Cn. Okay. Now, if we look these two, actually the difference between this norm of x and r can be written also. There is no point of writing the modulus here. You can write it this in this form. This can be, in fact, should be written like this, under root sigma I is 1 to n x I square, that is all. Why? Because they are real. So, x I square will be positive and we get, but here we have to use this mod sign, because they are complex numbers. So, mod of eta I must be real. So, this basically we can write this one, or mod x I, there is no difference with, but here you have to strictly use the mod absolute value of this complex numbers, okay, and then make the square. So, it forms the clear. Now, as a particular case, when you take R n equal to 3, then it becomes the vector space. So, when n is equal to 3, then the R 3 is the set of those point x, x I 1, x I 2, x I 3, such that x i's are real and the length of this mod x is under root x I 1 square, x I 2 square plus x I 3 square, and that is the length of the vector of vector x in the 3-dimensional plane, and which is nothing but norm of x. Okay. So, in particular we are getting the length, clear. Now, they form the norm space. Is it okay? Okay. Then we another examples. The space LP, LP, P is greater than 1. The space LP is the set of those sequences x, x i's are real or complex number R or C, such that sigma I is 1 to infinity mod x I power p is finite. Okay. And then introduce the norm x LP as sigma I is 1 to infinity mod x I power p raised to the power 1 by p. So, it will form the norm space LP. It can be easy to verify that this forms a norm space. And in fact, if I introduce the metric D x by h sigma I equal to 1 to infinity mod x I minus eta I power p power 1 by p, where x and y are the points in the LP space, then this forms a metric. LP under D is a complete metric space, metric space. Hence, LP with this norm is a Banach space. Because what is the definition of Banach space? We have introduced the Banach space as a complete norm space, and completeness is tested under the metric introduced with the help of norm. So, this is the metric which we have introduced with the help of norm, that dx by is the norm of x minus by LP, and that is equal to this. So, this way, because this is nothing but, if we take this part, it is nothing but this is equal to norm of x minus by LP, is it not? So, d of x by is defined in terms of norm, and with this metric it forms a complete metric space. Therefore, LP with norm P is a Banach space. Similarly, now here you see the elements are not vectors, are not, they are the infinite sequences. So, elements are real or the infinite sequence of real or complex number, and they form the
Banach space is a norm space which is again a complete metric space.
which is again a complete. And completeness, how to test it? Completeness means if a sequence Cauchy sequence converges, then it must be complete. So, when you say the Cauchy sequence converges, it means the converge to a certain point. So, slowly the distance between x and x keep on changing and reducing to 0. So, notion of the distance is important when you test for the convergence of the sequence, whether Cauchy sequence also. So, that notion of the distance is introduced with the help of norm. So, a space which is a norm space, if a Cauchy sequence, every Cauchy sequence also converges in the metric introduced with the help of norm, then such a space we call it as a Banach space, clear, a complete norm space. Okay. So, this is LP is one of them. Now, another example is L infinity. L infinity space, the set of all bounded sequences. L infinity is the set of all bounded sequences of real or complex number. Set of all sequences x, xi, I is 1 to infinity, where xi's are real or complex, and such that the supremum of this thing I is finite, that is set of all bounded sequences of real or complex numbers, and on it if we introduce the concept of the norm as the supremum of mod xi I over I, then this L infinity under this norm L infinity under the norm x norm infinity forms this one. This is a norm space, and not only this, it will be a complete norm space. It will be a, all the property of norms are satisfied, and if we introduce the notion of the distance dx by on L infinity as norm of x minus by L infinity, where x and y these are the elements of L infinity, then this L infinity under norm infinity L infinity, this forms a Banach space. Okay. This forms a Banach space, because under this it becomes a complete metric space. L infinity D is a complete metric space. So, this will be a Banach space, it is a complete metric space. Okay.
So, L infinity comma D
L infinity comma
D.
no
Complete metric space.
हाँ
Infinity, comma D.
हाँ L infinity comma D is a complete, this is a Banach space. So when you say complete metric space means L infinity D.
D.
Okay,
Okay.
it's complete metric space. Next is CAB, set of all continuous functions, set of all real valued continuous functions defined over the closed interval AB, and introduce the concept of the norm of x 1. I am introducing two norms here. One is maximum of mod x t d x t t lying between a and b. Okay. Another way, I am introducing norm of x 2 as integral a to b mod of x t dt, where the x belongs to CAB. Okay. Now, both these forms a norm, CAB under this and CAB under this are norm spaces. That one can verify without any problem. Both forms a norm space, because if you take the norm is greater than or equal to 0, because you are taking absolute value maximum of it, and if it is 0, then maximum of x t equal to 0 means the function x is such which is identically 0 over throughout the interval a b, because once the maximum value of the function is 0 for all t belongs to the function must be identically 0. Clear? Similarly, the other property, if you take alpha x, here the alpha comes, so mod alpha will come outside, and then x plus y, again maximum of the sum is less than or equal to sum of their maximum. So, again this is true. Similarly, here in this case, if it is 0 means this integral is 0, these are the non continuous function and no alternating function, because the absolute value is taken in consideration. A and b are two finite points, therefore, this has to be 0, x t must be identically 0 function. So, again all the properties we can verify its forms a norm. So, these two spaces, the same space under the two different notion of the norms forms the norm space. But if I introduce the concept of the distance notion here in D CAB with the help of first norm, but CAB with the norm D1, where D1 x y which is equal to norm of x minus y1 is a complete metric space, is a complete metric space, is a complete metric. That is, if I introduce the D1 h maximum of mod x t minus by t, t ranges over a and b, then under this metric it forms a complete metric space. Hence, CAB under the norm 1 is a Banach space. Is a Banach space. Okay. because this we have already verified in the metric space, then if the metric is defined in this fashion, it forms a complete metric space. So, corresponding norm is a Banach space. While the CAB with the metric D2, where D2 x y is introduced in terms of integral, is an incomplete metric space. Incomplete metric space. That is, when we introduce d2 x y as integral a to b mod of x t minus by t dt, then it is an incomplete metric space, is it not? That we have seen also by taking a Cauchy sequence in this form. Say here, when you start with this and then go like this, and in this fashion define between 0 to half, then this is half plus 1 by m and this is 1. So, between 0 to 1 the sequence x n is defined like this. It is a continuous functions, but it forms a Cauchy sequence, but it is not convergent because the limit point comes out to be discontinuous function. So, it is an incomplete metric space. Hence, the CAB with this norm 2 is not a Banach space. It is simply a norm space, but not Banach. And clear? Because it is not complete norm space. So, it is the incomplete norm space of this. Okay. Similarly, we can see other properties, other examples also. So, this will be so many things are there, so many examples one can say which forms the metric space as well as the norm space, and there are examples which forms only the metric space, but not the norm space. One of them is S, that we have seen. Now, this will be again we will have a general results under what restriction a metric, if it is introduced by a norm, what should be the restriction, so that one can obtain a metric with the help of the norm. That is, at corresponding norm space one can get the metric space with the help of that. So, that lemma a metric D, induced by a norm on a normed space, X norm, on a norm space X norm satisfies the following properties. Satisfy number 1, d of x plus z comma y plus z equal to d of x y. Second one is d of alpha x comma alpha y equal to mod of alpha d of x y for all x by z belongs to capital X and alpha is a scalar quantity. So, what this lemma suggests that if you wanted to test whether the given metric can be introduced with the help of norm, these two conditions must be satisfied. If any one of the condition fails, it means the metric D cannot be introduced with the help of the norm, cannot be induced by the norm. In the earlier case, when we have seen this metric, which we have S of yeah, if we look this metric which we have defined d of x by equal to 1 upon 2 I mod of x I minus y over 1 plus I, we have seen that this is a metric, but not a norm. It means that condition which we have introduced, both the condition may not be satisfying. Say example, if I take second condition introduce here. So, what will be the d of alpha x alpha y? What is this? This condition is says sigma I is 1 to infinity 1 by 2 I and then mod of alpha x I minus by I divided by 1 plus mod alpha x I minus by I, is it not? This will be. So, can you take alpha outside? You cannot take alpha outside, because as soon as you take alpha, this is 1 plus alpha. So, you cannot take mod alpha outside. It means the condition second y is not satisfying. So, this shows that if any one of the condition fails, then the corresponding metric cannot be induced by the norm. Let us see why it is so. The proof of this lemma is very simple. If a metric D is induced by the norm, then d of x by will be written as norm of x minus by, is it not? If the metric D is induced, if metric D is induced by a norm, then one can express dx by as norm of x minus by. So, what will be the d of alpha x plus z comma by plus z? Is it not the same as norm of x plus z minus by minus z? But z gets cancelled and finally, you are getting x minus by, which is equal to d of x by. Clear? Second part. So, first is to second, if d of alpha x alpha y, then this will be equal to norm of alpha x minus alpha y. So, this will be equal to norm of alpha x minus y, which is equal to mod alpha into norm of x minus y, because this is a norm. So, once it is a norm, alpha can be taken outside with the modular sign. So, we get this, which is equal to mod alpha d of x by. Clear? So, what we see that if a metric is induced by a norm, these two conditions has to be satisfied, and that is the criteria to judge whether the given metric can be induced by a norm or not. Okay.
So, one general question. So, some are called lemma, some are called theorem, some are called corollary, something like that. So, what is actually the meaning of this?
Lemma is a part, is a very some identity you wanted to prove it. Okay, that is the identity which are used for the further in the that we call it as a lemma or something, just small results you can say. But theorem is that when in general anything which is completed is in theorem a big, and corollary as a part of the theorem. Corollary comes means the result which can be obtained with the help of the theorem. Lemma is used proof in which is helpful in proving the theorems. So, that is why. Okay. It is not that barely weak important results, we call it as it something. Okay. So, that is. Now, the another concept of this metric space, we have the subspace and the corresponding sequence. So, definition of the subspace or sub norm space. of a norm space. A subspace by of a norm space X norm is a subspace of X, is a subspace of X considered as a vector space. Vector space with the norm obtained by restricting the norm on X, to the subset Y. Okay. This norm on Y, is said to be induced by the norm on X. The subspace of a mean, if X be a vector space, and then if it is also a norm, a notion of the norm is introduced. So, X with norm is a norm space. A by which is a non-empty subset of X, this will form a norm space, a subspace of a norm space, if the by with addition and multiplication forms a vector space, that is by must be a subspace of X, and the restriction of norm on by of the norm of X, when it restrict on by, then this restriction under this by must be a norm space. That is, this norm must be the restriction of the norm of X on by. Clear? This is the norm of X on by. So, we are denoting norm by. Clear? So, in this norm it is a norm space, it is a subspace, then we call it. Then how to define the subspace of a Banach space? Subspace of a Banach space means it should be simply a subspace of that space. It need not be, if X is complete, by need not be a complete space. Okay? So, subspace of a Banach space we mean is simply a subspace of X considered as a norm space. Okay? So, subspace of a Banach space is subspace of a Banach space X is a subspace only considered as a subspace of X considered as a norm space, not a Banach space. Okay? So, this is important. Clear? Means that concept should not be in mind, that because we are taking the subspace of a Banach space, so subspace should also be a Banach space. Not so. It simply must be a norm subspace, that is all. If in addition it is also a Banach space, that is different matter. Suppose it is a closed, by is a closed subspace of a Banach space, then it has to be a Banach also. Clear? But the condition in defining the subspace of a norm space, the completeness is not required. Okay? It's okay. Thank you. Thanks.